So this section is going to build on the rational functions that we did in the first part, but it kind of kicks up a notch. There will be some that will be a little more realistic and then some that get really crazy. The really crazy ones, we will deal with them a little bit in the homework, but not as much on the test. So let's go ahead and look at this one. Again, looking at, first of all, where are our x asymptotes? So that would be our vertical asymptotes. We take that denominator and say, what makes that equal 0? Now, this is a semi-complicated one. It's not just a single answer. I could try to use a quadratic formula on this, but what I'm going to do is I'm going to check and see if it factors. So I'm going to go back to AC. So 2 times negative 3, I'm looking at factors of negative 6 that can make a 5. Maybe either 1 and 6 or 2 and 3. To make a positive 5, the 2 and the 3 would have to both be positive. That won't make a negative 6. That's not going to work this time. The 1 and the 6 could work because then they have to be, if they were opposite signs, I could use a negative 1 and a positive 6. Then what that would do is that would still multiply to make the negative 6. So we split this, negative x plus 6x. Factor by grouping, these have an x in common. Factor by grouping, these have a 3 in common. So now we can factor out 2x minus 1, leaves us with x plus 3, setting each of these groups equal to 0. For the first one, we get 1 half. For the second one, we get x equals, what's that, negative 3. So again, this is going to have 2 asymptotes. One at 1 half, and one at negative 3. How do I get the horizontal asymptote? I recommend thinking about these as, and first of all, I wouldn't even be able to do a long division on this one. So you really need to think about, for the horizontal, think about what happens when x gets big. That's where we get asymptotes on these types of graphs. So everywhere there's an x, we're going to put an infinity. As x approaches infinity, what happens to the y? Well, we have infinity plus 1 over 2 infinity squared plus 5 infinity minus 3. On the top, what's insignificant? If I've got infinity dollars, I don't care about plus 1. On the bottom, what's significant? What we do is we only keep the highest power of infinity. We all understand and hope by now that the minus 3 doesn't even make a drop in the bucket, right? But if I've got infinity squared, if I've got a billion times a billion, if I got a billion billions, this 5 infinity actually becomes insignificant. So we just keep the highest power of the infinity, and then we simplify what's left. Well, what happens this time, though, is when they simplify, I'm left with a 1 on the top and 2 infinities on the bottom. Whenever we have an infinity in the denominator, we talked about this before, when I divide by really, really, really big numbers, then it approaches 0. So this will have a horizontal asymptote at 0. So we said, what was this? X cannot equal 1 half, x cannot equal negative 3, and y cannot equal 0. Those are our 3 asymptotes. What does this graph look like? We're going to check points around the region. So we're going to check, if I check x equals negative 4, we get on the top negative 3 over 2 times negative 4 squared plus 5 times negative 4 minus 3, I don't know, 16, 32, minus 20 is 12. negative 3 over 9. I don't really care as much about the number. Here's what I'm seeing. When x is negative 4, the y value is negative. That tells me we're down in this region. Because when x is at negative 4, the graph is down below that asymptote. Past 1/2, x equals 1. Again, I don't really need the number. I just need to know what region is it in, top or bottom, right? If I plug in a 1 on the top, 1 plus 1 is 2. Over 2 times 1 squared plus 5 times 1 minus 3. We get 2 over 7 minus 3 is 4, 2/4. I don't really care that that simplifies to 1/2. What does this mean? We are in this top region. Now, I've done enough of these to know that what's going to happen in the middle is this little S shape. But if you haven't, then what you're going to have to do is you're going to have to check those numbers in the middle. So when I get these two, I know the middle is going to do that little S shape. So I need to check negative 2. So that would give us, what is it, negative 2 plus 1. So negative 1 on the top over 2 times negative 2 squared plus 5 times negative 2 minus 3, 4, 8. I think I get negative 1 over negative 5, which is positive. I don't need the exact number. All I know is that at negative 2, the graph is somewhere up here. At 0, again, I'm just going on the other side of this netting right here. To the left of it is 0. If I just plug in a 0, I get 1 over 0, 0, negative 3, negative 1/3. What does that mean? Well, at 0, the graph is down in this region. So what is it doing in the middle? It does this weird little shape. Let's double check this one. I know it's a bit messy, but that would be, again, how I would learn to sketch these by hand. So x plus 1 over that x plus 1 on the top, 2x squared plus 5x minus 3 on the bottom, and here's our graph. Asymptote here at 1/2, the other one's at negative 3, lower region, upper region, little cubic symbol in the middle. Let's see how we did. Oh, they do talk about the domain again, so we should do that real quick. It's a good thing I'm using these notes and not just going on. So what happened to the domain here? Well, it had 2 holes, right? It went from negative infinity, but then it stopped at negative 3. There was our first asymptote. And then it went between negative 3 to 1/2. And there was a hole there. And then it continued from 1/2 to infinity. So it's going to have 3 separate regions, okay? So notice 1, 2, 3 separate portions of the domain. And we had to check all 3 of those sections to kind of sketch that by hand. Our range, up forever, down forever, but had a hole at 0. So from negative infinity to 0 with a hole, and then picking up at 0 to infinity. So here's our restrictions on x. Here was our domain. They do a weird, different example of how to check the horizontal asymptote. I like to just do it with infinity, so kind of a different approach. Finding the asymptotes analytically, and we're on a different question. Excellent. So we've already I've been trying to prep you for this, but like the easy one is we take the denominator, we set it equal to 0, we say, well, then x can't equal 3, right? That would be our vertical asymptote. The horizontal one, I could look at this right now and tell you it's 2. That's way easier than having to do the whole long division. You could actually do the long division, but you won't be able to on every question. So how the heck did I know it was 2? Replace x with infinity. As x approaches infinity, I'm going to argue y approaches 2. How do I know that? Put the infinities in there. Get rid of all the insignificance. Reduce what's left. And y cannot equal 2. It gets really close, but it never will equal 2. Okay? Then it's just a matter of sketching this out. X cannot equal 1, 2, 3. Y cannot equal 2. Our A is positive, so I'm going to say probably this region and this region. But I would still check. I would check. An easy one is where x is 0. If x is 0, we get 1 over -3 or -1/3. That puts it, well, really down here. So my sketch kind of sucks, but the idea is what? It's still in this bottom region. So I can kind of clean that up, I guess. If I check past it, 1, 2, 3. Well, I can't check 3, I'd have to check 4. I would get 8 plus 1 is 9 over 1. Where does that put it? Up in this region. So if you can get really good at just thinking about the infinities, you can find both the vertical and horizontal asymptotes on some of these really quickly. See how we did on that. Solve it for 0. Domain, all the numbers except 3, so we've talked about that. I'm not going to do that one again on this one. And again, I don't like to do what they're doing here. I do the infinity. That to me seems way easier than this. Plus, we really do think like that a lot during calculus. We kind of think a lot like that. Domain and asymptotes of this graph. We'll get through this one pretty quickly as well. So x squared plus 1 over x minus 2. Is it right there? Okay, this one you need to kind of put a big little star on. This we're going to introduce what's called an oblique asymptote. Okay, and we'll talk about what that means in just a minute, but let's start with the easy one. We know the denominator cannot equal 0, so x cannot equal 2. Done. 1, 2. So what about our horizontal? Well, if I put, this was the vertical, for the horizontal, if I put an infinity, get rid of the insignificance, cancel, I have 2 infinities over 1 infinity, leaves me with infinity. Here's a problem. Y approaches infinity. What does that mean? This graph is going to basically come down and then go back up forever. So how do I fix that? Well, it doesn't have a horizontal asymptote. Because it ends up coming back up. And if I do the same thing with negative infinity, it would just make it go negative infinity. But basically, I need to find what's called an oblique asymptote. And what this means is that we have an asymptote that is basically at an angle, okay? Or like a linear equation. And it's not that hard to get. What you do is you take the numerator, the x squared plus 1, and you divide it by the x minus 2. So this is how you're going to get obliques. When there is no horizontal asymptote, divide. X times what is x squared? Multiply and subtract. X squared minus 2x. Subtract, makes them all change signs. I'm left with 3x. 3x divided by x is just what? 3. Multiply. 3x minus 6 and subtract. Change the signs. So we have x plus 3 with a remainder of plus 6 over x minus 2. So what does this mean? Well, think about it this way. If x approached infinity, if I were to put an infinity down here, then this whole part would basically zero out. And the graph would act just like x plus 3. It would act like infinity plus 3, but it would act just like the equation x plus 3. That is called an oblique asymptote. Basically, y will never equal, but it'll start, as x gets really big, it'll start acting like x plus 3. That's an asymptote. It's just a linear equation. Look, with a y-intercept of 1, 2, 3, and a slope of up 1 over 1, up 1 over 1, it is an oblique asymptote. So then what does the graph look like? Well, I'm going to check regions. It's either going to be here in that netting or here in this netting. How do I know which one? Check regions. We've done this before. So I need to the left of 2. I could just check 1, but I'm going to check 0. I like 0 on this one. So I'm going to check here if x equals 0. 0 squared plus 1 is 1. 0 minus 2 is negative 2. We got negative 1/2. The graph goes at 0 down here to negative 1/2. That tells me it's in this region. It also tells me it's going to be up here in the top region. I've done enough of these, I know the behavior, but if you're not sure, plus you could have made a mistake. So I'm going to check x equals 3. On the top, 3 squared is 9 plus 1 is 10. On the bottom, 3 minus 2 is 1. So we got 3, 10. So 3 way up here at 10, that tells us the graph is up in this region. Let's see that one on the calculator, because I know that can be tricky. X squared plus 1 over x minus 2. What do we say? X squared plus 1 over, no, that won't work. There we go. Try that. Over, I don't know why that one looks all slanted. Dang it. X squared plus 1 over x minus 2. Now we only see the left side here. It has our asymptote. Did I do that right? Minus 2. Yeah, so it has that. The graph is kind of down in this lower left region like we thought. I don't see the right region. It's just a little taller. It's up here, but that's where the second part is. So what is this graph doing, right? It has this diagonal asymptote. At what? Well, we said it was at x plus 3. Which means what? Did I mess that up? No, we said it was x plus 3. Maybe I typed something in. X squared plus 1 over x minus 2. I don't know. It doesn't look quite right. Basically what? The graph's going to get closer and closer and closer, but never reach that asymptote. As x gets really big, these two end up being the same. I'm going to check one more thing. Something doesn't seem right on that. Oh, I messed up. That's why. My oblique asymptote is wrong. These don't, and I hope you're screaming at your computer screen. That's a rookie mistake. Those are not like terms. Shame on me. Bugger. Let's try this again. Bring this down makes 2x plus 1. Those are not like terms. X into 2x goes in twice. Makes 2x minus 4. subtract gives us plus 5 as the remainder. 5 over x minus 2. So my oblique asymptote was not x plus 3. Our oblique asymptote was x plus 2. Oops, it happens. Let's fix that just to see. Now they're looking like they're lining up. And look, they get pretty dang close where they're practically the same line. As x gets really big. If I go the other way, it lines up, gets closer and closer and closer. And so that, I gotta fix this picture up here, dang. It's a little things. At 2, and the slope of 1, that creates that second netting. Y cannot equal x plus 2. It'll get close. So that's called an oblique asymptote. So we already knew the denominator. I didn't do the domain on this. We've done that to death. So we did the vertical asymptote. How do we get the horizontal? They said it approaches infinity, so this isn't working anymore. So do the long division, and we get x plus 2. So that is called our oblique asymptote, neither vertical nor horizontal. This is a little bit better of a picture than what we did. Vertical, oblique, and then it stays within that netting. So then we just have kind of a quick review, and I'm just going to go through these if you want to slow down and write down some stuff. But we've done vertical asymptotes. Take the denominator equal to 0 and solve it, right? As long as it has a 0, it will have a vertical asymptote. How do we get horizontal? I don't do it this way. It's all crazy. I do the infinity, okay? And then if that doesn't work, then I do the oblique or slant asymptote by dividing it out. Graphing techniques, I'm not as worried. I would just do what I'm showing you here. That should be good. We do the vertical, horizontal, oblique, find out the regions, and sketch the graph. That's how I would handle it. A couple more examples before these get to the crazy ones, but these are mostly what you're going to be seeing on the test. If I have a crazy one, we'll be using our calculator. That'll be in the calculator section. Because you'll see they're hard to know what's going to happen by hand. But this was one we could do by hand. Let's start with our vertical. Our denominator cannot equal 0. Adding 1, x squared cannot equal 1. Square rooting, we get 2 vertical asymptotes because this square root we put that square root. So we put plus or minus down here. So this will have 2. 1 at 1, and 1 at negative 1. How about the horizontal? So that was our vertical asymptote. Horizontal, my first go-to, is to replace x with infinity. 2 infinity squared minus 1. What is insignificant here? Not the multiplication, get rid of the adding and subtracting. Then reduce infinity squared over infinity squared, and y will never really equal, but get close to 2. What does this graph look like? Check regions. We have to the left of 1 would be, or negative 1 would be negative 2, positive 2. 2 times negative 2 squared, negative 2 squared minus 1 is what, 8 over 3, 8 thirds, 2 and 2 thirds. That just means it's up here, above the 2. If I check x equals 2, 2 times 2 squared minus 1 8 over 3. That one's also up here. So what's the middle going to do? I know it's going to be a little parabola. I've done enough of these. If you're not sure, get a little trickier, but you have to check. But the only problem is the only number between -1 and 1 is 0. And we get 0 over -1, which means really this graph crosses, if I want to be more exact, right here. But what does it do to the left and to the right? Well, I'd have to check. X equals 1/2 and x equals -1/2. Those are not fun numbers to check. So what we really are worried about is not whether this is what the exact number is. I just need to know, is it positive or negative? Well, on the top, this is 1/4 times 2, or 1/2, over 1/4 minus 1. That's -3/4. A positive divided by a negative, y is negative. I don't even need to know what the number is. That tells me that up here, this graph is going to go negative. And if I do the other one, it will also do the same thing. So here's the sketch that they had. They had the 1 and the -1, and they recommend checking those numbers. I don't need to be that exact. I knew crossed at 0 and on both sides was negative. I just need the region. Where in the netting is it? If I want more exact numbers, we'll use technology. Let's do another one. We'll start with our vertical asymptotes. Take that denominator. Set it equal to 0. Good news on this one is that it can factor. What multiplies to make 16 combines to make 8. How about 4 and 4? So basically, when I take each of these groups and set them equal to 0, I get the same answer. I get that x equals -4. So even though this looks like it has a double, it really only crosses at 1, 2, 3, -4. Just here. Okay? That was our vertical asymptote. How do I get a horizontal? Replace everything with infinity. 3 infinity squared minus 3 infinity minus 6 over infinity squared plus 8 infinity plus 16. What becomes insignificant? The adding and the subtracting. If I have infinity squareds, regular little infinities become insignificant. I keep just the highest power, keep the multiplication, reduce what's left. Infinities all cancel, leaving us with just 3. Y will never equal, but get close to 1, 2, 3. So now we're trying to figure out kind of the netting on this. Okay, what region? What region do we graph this in? 0 would be an easy number to check. I get, what is that, -6 over 16. That's negative. That's down here. That makes me think, I guess, this graph goes down here. As I check 1, 2, 3, 4, -5. 3 times -5 squared minus 3 times -5. Is that -6? Oh my. All over -5 squared plus 8 times -5 plus 16. On the top, what do we have? Geez, 75 plus 15 minus 6. 90 minus 6 is 84 over 25 minus 40 plus 16. I think that's just 1. Yep. So positive. Jeez. Way up here. And let's double check this one. Crazy, crazy one. What the hell happened here, right? We got this region right, but down here, what is going on over here? This is where we're going to have some strange things happen where they don't really fit the other patterns. I thought it would be down here and here. I checked 0 and it was down there, right? But what happens is if you check numbers closer, it would have actually been up here. So this graph, what it actually does, I'll change the color just to be significant, is it starts up here and it goes down and then it comes back up to where we, so it does this really weird kind of loop in the middle. Like, what is going on here? It's just not fitting our regular pattern. This happens sometimes basically where we would have had another asymptote, but we didn't because it was like a double asymptote. Don't stress about this. Use your technology. This would be the type of question where we go through and we do all the work, and at the end, this asymptote's not wrong. It just crosses it right here. So don't freak out about it. This happens sometimes. The weird ones, we will have technology for. Weird, weird, weird. Let's keep going. I think I got one more weird one. Oh, I got a couple. X squared plus 1 over x minus 2. Did we already do that one? We already did that one. I'm going to go ahead and just come up with that other one real quick. And let's just say we're going to try to graph this. Okay? So, again, denominator, x cannot equal 1. There is our vertical. Okay? Horizontal. If I put in infinities, get rid of the insignificance, cancel, I'm left with 3 infinity. This does not have, this is one where it starts coming down and goes back up. At y goes to infinity. So how do I find that? Well, when that happens, you have to find the oblique. How do we find the oblique? Take that 3x squared plus 1 and divide it by x minus 1. X times 3x, 3x squared, what is that? Minus 3x, change the signs. Leaves us with, I'm not going to fall for this again, about 3x plus 1. 3x divided by x is plus 3. 3x minus 3, change, gives us plus 4. So that's our remainder. So what is the oblique? This right here. Our oblique, y will not equal 3x plus 3. What does that look like? It has a y-intercept of 1, 2, 3. It has a slope of 3 over 1. And then we need to check the region. So let's check x equals 0. Gives us 1 over negative 1. Down here. There's our first region. Then our second region must be up here. How do I check that? The other side of that would be 2. 3 times 4 is 12 plus 1 is 13 over 1. So way up here at 113. Okay? I'll double check this. 3x squared plus 1. over x minus 1. We definitely saw that. This is the region we thought it would be in. This one's way up here. There's that top portion. And we said this would have an asymptote to 3x plus 3. So that is our oblique asymptote. It's not pretty, but that would be enough. So for this next one, this is another one of those kind of weird ones. I just have a couple more weird examples coming up. But when I do this, basically, I take that denominator, say it cannot equal 0, right? Which means x cannot equal 2. How about negative 2? Getting to be a rookie on these things, gotta be careful, right? When I do that was vertical. When we do the horizontal, infinity square root of minus 4, infinity plus 2, get rid of the insignificance. We're left with infinity. This has no horizontal, which means our next step would be to check for oblique. If I do x squared minus 4 divided by x plus 2, x times x is x squared, what is that, plus 2x, and then subtract, makes that negative 2x minus 4, put in a minus 2, makes that minus 2x minus 4, change the signs. This one had 0 remainder, that's weird, but that's still technically an oblique right there at x minus 2. Interesting. So y-intercept of negative 2, and a slope of up 1 over 1, up 1 over 1. So it's tempting to kind of do our little obliqueness, right? I already told you this was a special one. Because there was no remainder. Basically what's happening is, if I had x squared minus 4 over x plus 2, I could have factored that x squared minus 4 to make, let's see, x minus 2, x plus 2. So what can happen with the x plus 2's? So basically this graph acts just like the x minus 2. But there was still a hole with the vertical asymptote. So what the graph ends up looking like is just like this x minus 2. But how do I show that hole? Put a little open dot there. You don't have to believe me, I can show you this one. X squared minus 4 over x plus 2. X, let's see. Over x, was it minus 2? Plus 2. Plus 2. It acts just like the equation x minus 2, except there's an asymptote right here at 0. You don't see it, but it's right there. Here, I'll show you. If I add the table, I can look at when x is at, what was it, negative 2? This graph is undefined. There is a hole right there at negative 2. You have to catch that. So note that it still has an asymptote there, but it acts just like the line and ends up with a hole right there. I must have copied it down right. Yeah, I didn't copy it down wrong. That's okay. Same idea. The last one is going to be if we have 1 over x squared plus 1. So we take our denominator and say it cannot be 0. Well, subtracting 1. X squared cannot be negative 1. Square rooting. X cannot be plus or minus the square root of negative 1. X cannot be imaginary. Okay? Where is the imaginary number on this x-axis? This doesn't exist. So what this means is there's nothing that can make that denominator 0. This has no vertical asymptote. Check horizontal. 1 over infinity squared plus 1. Get rid of the plus 1. 1 divided by a really big number gets really close to 0. There is a horizontal asymptote at 0. So what is this graph going to look like? Well, basically, it's going to be getting close to 0 to the right and the left, but what does it do in the middle? Normally it does these little shapes, right? Well, let's check. What happens when x equals 0? What is 1 over 1? It crosses at 1. What happens if x equals 1? 1 over 2. 1/2. If x equals 3. 1 over 10. It's getting smaller, so this is where it's going to go down and get closer and closer, but never cross that horizontal asymptote. What happens to the left? If x equals negative 1, I square it and I get 1 over 2. If x equals negative 2, I get 1 over 5. It does the same thing. So it comes up, but it never has an asymptote, so it just goes right back down. Kind of like a little hill, okay? So again, this is not one I'm going to be expecting you to just recognize. This is one we will be using our technology to do. So 1 over x squared plus 1. One over x squared plus 1. And it just comes up like a little bloop, just like a little hill right there. And that's it. So those are kind of the crazy graphing of rational equations that you're going to see. The first section was mostly the types you're going to see. The second one, we're going to have some of those on the test, but these last ones where they act strange, kind of the exceptions to the rules, if they do show up on the test, they will be in the calculator section where you're not going to get caught by those. You still need to be able to check all of the asymptotes, vertical, horizontal, oblique, check regions, know where to sketch it. We'll keep reviewing, but that's it for this section.